Okay, homework. Any questions? How many of you are done? So we got 3 in the front row and 1 in the middle row. Okay, so clearly people are not done with it yet. So no questions on it? You guys will knock it out of the park. You guys are not talkative today. I mean, I told her, I said, well, you guys, they never seem to want to talk. And she goes, well, do you think they're afraid of you? I go, I don't know. Like, I don't think I'm a scary guy, but, and then she goes, well, if you have to say that, then maybe you are scary. Okay. I guess, right? Doth protest too much, right? What?
We need our daily joke.
We need our daily. Oh, dang it! It's in my other coat, so I brought Laffy Taffy today. I was gonna read Laffy Taffy jokes. You're right. We need a joke. That's the only way I can get you guys to laugh.
I got this. I got a really funny joke.
You got a really funny joke. Okay.
My little brother sent this one to me, and I laughed for way long. So everybody knows why 6 is afraid of 7. It's because 7 ate 9. But why did it choose to eat 9? Because it needed 3 squared meals a day.
It needed 3 square meals. There you go. That's a good one. See if we can find. We'll find another one. See, maybe I'm not such a scary guy. Oh my gosh, that one's long. That sounds. Let's try a different one. I've got contacts. See, and then they have lame ones. Why did the dog sit in the shade? Because he didn't want to be a hot dog? Oh, come on. See, my son told me the one. He goes, knock, knock, who's there? Boo, boo hoo, why are you crying? So he did that one. But the favorite knock, knock joke that I have is, I'll tell it. Bryson, you can. So knock, knock.
Who's there?
Banana. Knock, knock.
Who's there?
Banana.
Banana.
Knock, knock.
Who's there?
Banana.
Banana.
Knock, knock.
Who's there?
Orange.
Orange shoe.
Orange, you glad I didn't say banana? Oh, come on. It was good.
That's not original.
How many jokes are original?
You have to repeat it.
What?
If there's a loop.
If there's a loop in the joke? But it's the rule of 3, right? You got to do something 3 times before it's funny. See, it made you smile despite how lame it was. You guys are telling jokes and I don't even know the punchline. All right, so last time we talked about arrays, right? So we can have arrays, 2-dimensional arrays. And so it's like a grid. We have rows and we have columns. And we can name things, awful variable names so that they don't make sense, so that when you try and go through it, you say, what's a custard? I don't know. It's kind of like a row, but not. I mean, it's always good to name things that are good. Now, I previously taught at a university that had lots of people who were hackers and considered themselves hackers. And so they like to go counterculture. So, like, I had people using the F word for variables, and I told them that was not acceptable. So I don't appreciate that, but, that's what some people do. So, no swear words as variables. That's one of my rules. Also, I don't swear in class, but I guess that's separate. All right, so we have the ability to go through and create these arrays. Now, we did two-dimensional. You can also do three-dimensional, though when you imagine 3 dimensions, right, I guess it's easy to imagine a cube, right? So you have rows, columns, or maybe an easier term if you're math, right? You have the x-axis, the y-axis, and the z-axis, where z sort of goes back, right? And you could have 4-dimensional arrays, and so then you start having to think about, well, I can have like a cube, right, which is 3-dimensional arrays, and then I have a series of cubes. So you can think of that, or you can think of it as time. And so we can do as many dimensions as we want, but 99% of the time, it's either a 1-dimensional array or a 2-dimensional array that you'll ever have to deal with. And we can represent a lot of things with 2-dimensional arrays. So for example, what's a 2-dimensional array that you guys may use a lot? Or maybe you don't, I don't know. What's something in 2D that you use in real life?
Calendar? Or is that not what you're looking for?
Well, you could think of that, I guess, in 2 dimensions, right? So that's something that you use. Right? If we talk about maps, so what do we use to figure out where somewhere is on a map? Longitude and latitude. And what do those mean? It's kind of like that, right? So does anybody know what our location is? Let's see if I can, I'll click on something. Where's a marker at? UNK. So if you are in something like Google Maps, right, and I clicked on the little marker thing, right, we have our longitude and our latitude, right? So I think the border between us and Kansas is at -100, right? So that's where at like negative. Is it? I think it's. Well, maybe it's 40. Maybe that's it. All right. So longitude and latitude are based on where you are from the prime meridian, which goes through. Is it go through Greenwich?
Yeah.
England, right? Right, so this was a city that is 0 degrees longitude, right? And then latitude is how much up and down from the equator you are, so how many degrees up and down you are. And anybody know what else is based off of Greenwich other than longitude? Like clocks. Is anything on clocks based on that? Anybody know what that's called? Zulu, which I'm not exactly familiar with that one, but okay, I guess it's a military version. GMT. So GMT is Greenwich Mean Time. So basically, the clock there is, they say GMT plus 0, right? So it's 0 hours in front of Greenwich Mean Time. Right now we are, I think, -8. Let's see, 3, -6. Maybe that's what we are, -6. All right, so when people want to schedule things, or when computers talk about time, they talk about time in terms of Greenwich Mean Time. And then your time zone is some offset from that. So we are, I think, must be -6, right? So 325 minus 6 is 925 or 926. And so that's what time we are based on. And so that's another Interesting thing that's based on Greenwich, England. So that's our longitude and latitude, right? And those are stored. And so when you are thinking about, well, how do I navigate from one place to another, right? We use coordinates, and then we have these things that connect spots, which are called roads, or pathways, or when you get into mapping, you'll learn that there are places that are only accessible by ferries, right? And you have to get on a ferry to go from one place to another. So when I was working, we would have a bunch of stops that our trucks would have to make, and so we would have to figure out a route for them and how long was the route. Funny thing was that if you would map it in one program and then you go to another program, so we'd have like MapQuest and then we'd have Google, they would give you different numbers for how long it would take. They would give you different routes. Does anybody know why, one of the reasons why they would give you different numbers or different routes?
Does one like account for traffic and stuff, the other one doesn't, or
They could be accounting for traffic. There's also another funny thing if you ever talk about people who make maps, that the person who makes a map will actually add things that are fake into it. So why would they add something that's fake into a map? Copyright. So if you copy it and you don't know that it's fake, right, you'll copy that artifact and then all of a sudden it's very obvious, hey, there's this made up road here that doesn't actually exist, and you put it in your map and they put it in their map, right? So that's one of it. Another one is sometimes maps are smart enough to know that some streets are one way and some streets are not. And so, right, they'll have you go down a one way, which thankfully a lot of the time right now that's a good thing that they've figured out which streets are one way, which are not. Or the example with the ferry, right, there are some times where you could use the ferry if you went at a certain time, but then if you didn't go at that same time, right, you'd have to take a road that goes like out of your way to get there. So maps are something that we very much talk about in 2 dimensions. And so we could use what we have here to, right, so we made a triangle last time. But one of the things that if you talk about, let's say robotics, right? So some of you will take an AI class. So when you have some sort of robot that is trying to navigate, right, it might be that you're given a map that has, right, some obstacles on it, and you might be at spot, I won't use an X, and you may want to navigate to that, but you have to sort of negotiate the fact that there are obstacles in the room, right? And this is what people do all the time, right? We're actually pretty good at avoiding obstacles when we're not looking at our phones, right? And when we do look at our phones, we're less good. I saw that there was some city was going to make a law against zombies in the fact that people walk around staring at their phones, not looking up, so they're like zombies, because zombies, right, are getting into accidents. I think they just wanted to like say zombies in a law, but that's just me.
I think there was a city in China that made a walking, like a texting lane on the side.
A texting lane? I had not heard of that. They also do a lot of different things. Like they actually use QR codes. So anybody know what a QR code is? If you actually looked at that poster, right? That thing down there is called a QR code. So QR stands for quick response. Funny story is I actually used QR codes in my PhD thesis. Right? So I actually talked about communication using QR codes. So these are the 2-dimensional barcodes. If you go and get a scanner, right, you can search for scanners on your phone. You can scan QR codes and read what's in them. But they actually use them to send information a lot, right? So you'll see them around campus every now and then. But they're actually very robust, right? So like you can obscure parts of them, and they have error correction built into them, so that figures it out. So what I'd like to do today is sort of build a maze, right? And I see in the book that this book is so heavy. They talked about random numbers. So we're going to generate a random maze today, and then we'll talk about what are ways that we could navigate through our maze. But we may not get to those at this point. So I'll call it build a maze. Okay, so if we're going to build a maze, right, again, I see things on TV. Like I saw that Build-A-Bear was like doing teddy bears that are like Star Wars that you can like flip in and out. So build a maze. Okay, so we should know the arguments to this, right? We're going to do some sort of array, and we have to give it the size. Yeah. See if this will work. Doesn't want to do it. Okay. I can't spell. I'm going to give it one more argument. And that's how many obstacles do we want to give it. So let's say we do 10 for this one. I probably spelled that wrong. Again, another thing you learn if you take my classes. My ability to spell is near 0. It's not very good. All right. So, you guys all read the book. Anybody remember what the class is to generate random numbers? Random. Thingy. Bob. Okay. Oh, and I can't use dashes. Dang it. Underscores. So totally better. This is a phrase comes from my child. Thingy-mabobwa apparently is a word that he uses at school. I have no idea, but. All right. So this is it generates random. Did you guys do anything in lab with random numbers?
We're doing it this week.
That's this week. All right. Perfect. All right. So the way that the random number generator works is we have what are called pseudo-random number generators, right? So it's a generator that'll create random numbers, but if you take the output of it, right, it's actually, if you give it an initial condition, it's actually the same every single time, right? So it'll give you the same sequence of random events, but we can, if you look at the constructor, it said that we could give it a seed, right? So that's an integer. And so that's basically like, we're going to start at a random place within the, what we call pseudo-random number generator, because if it's pseudo-random, that means it's not actually random, but it's mathematical. But if we give it a random place to start, then it behaves as though it's random. And there are actually ways where you can get actual, what we call entropy. Right? So entropy is how much noise do you have in some set of numbers, right? So if you have 0 entropy, it means that you can always predict the output. It means like, I generate a stream of numbers, it's always 1, right? So what's the next number in the sequence? You know, if I did 99 of them, the next one is going to be 1, right? With 100% certainty, I have that. Right? So that has 0 entropy. Now, 1 entropy is completely random. So does anybody know something that is completely random? 47. No, it's not. It's not. 42. Okay, that's completely not random because it's the meaning of life, the universe, and everything. Right? So there are things that are complete, that are random in the sense that we can't predict what they're going to be. So I can give you some examples. So how many of you have had a TV that's hooked up to an antenna, and then you turn it to a channel that doesn't exist? Right, that stuff that you get on the screen, right, that's noise, right? It's random. They actually also will use the output of lava lamps. So lava lamps, right, the goop is like going up and down. So there's actually, I can't remember if it's Oracle, one of the big tech companies has like a wall of lava lamps. So you walk in and you see this wall of lava lamps. And then behind each one of them basically have a camera. And all it's doing is reading in that data, and then they just take part of it, the like end of it that's kind of random, the least significant bits. And then they take that and they feed that into their random number generators, right? So that's actual random noise, right? You can look at signals coming into your computer, what time interrupts come in, how fast the clock is. There's a lot of pieces of computers that are random, and then you can put those together to generate something that's actually random. So this one isn't actually random, but is it current time? Right. So generally, if you want to generate something, right? So we talked. What is the current time, millis? What is that?
Time after start of program.
Yes. Well, no. It's not the start of the program. I think I told you guys at one point. I remember.
Oh no, it's after the start of the one computer.
The one computer. We call it the epoch, right? January 1st, 1970. Right? So that's when computers time, right? And every millisecond, right? Every second we get 1,000 milliseconds. Right? So if I run this now, it's going to have one time. If I run it in 3 seconds, it's going to have a different number. Right? So this number is always changing, so I won't get the same output over and over again. So that's good. So that's our seed, right? That's where we're going to start is, hey, just pick the current time, and we're just going to use that. So now, thingy-mabobwa, right, returns stuff. Right, so it can return a long, or it can return next. Let's go with a float. Does it have double? A double. So let's see what that does. Hover our mouse over it. Returns the next pseudo-random, so it's not actually random, but we can think of it as random. Right? Number between 0 and 1. Right? So what we'd like to do is we'd like to generate a random row and generate a random column and then put something there. Okay? And how many times do we need to do that? Am I going to use the number 10? I'm going to use the the variable obstacles, right? At this time it's 10. Next time it might be 100, right? Well, that would be like everything. Well, mostly everything. Okay, so how would whatever I'm going to do, I'm going to do it obstacles number of times, right? What would I type to do something obstacles number of times? For loop, right? Here, we'll do it a different way. I'm going to do while obstacles is greater than 0, and then each time I'll just decrement the number of obstacles I have left, right? So that represents how many do I have left? Right, so I'll have to generate my thing, and then at some point decrement obstacles. Okay, so I generate some random number between 0 and 1, but really I don't want it to be between 0 and 1. I want it to be between 0 and 9. So how could I scale up my random number? Right, I don't want it between 0 and 1. I want it to be 0 and 9. So I really need to make it like 10 times bigger. But what if the size of my arrays was 100 by 100? then I'd want it to be that much bigger. What mathematical thing could I use to scale something up? Theoretically, I could use exponents, but that would give me, okay, my number, let's say, is 1. Well, if I do 1 to the 10, I get, what's 1 to the 10? I get 1. Okay, exponents maybe not the right thing. Some other mathematical operation where I can increase the size of something directly proportional to its original size. I should have brought candy, and I could throw stuff at you. Multiplication! Oh! So if I multiply it by size, right? Now it's 10 times bigger, right? So now I have a number between 0 and 10. Great. So I could turn that into a row. And why is it going to complain? Anybody want to guess? One side's an int, one side's a double, and it's like, whoa, you're going to lose precision. Watch out. Alert, alert. Okay, let's just, yeah, we know we're losing precision. That's okay, right? Because, right, rows and columns have to be whole numbers, right? They can't be partial numbers. So we do the same thing for the column. Right, and we just get the next thing that comes out of our random number generator. And then how do we set the character at row and column inside of array to be, we're going to use X. Heather, you want to take a shot at it? What? You can just guess something, right? Clearly nobody else wants to try, so take a guess. I want to set the character inside of array at row and column to be an X. So how do I access array at row and column? Yeah. Okay, and how do I make that become an X character? I give it character X, right? There we go. Right, see? Wasn't that hard. Everybody else is just chicken. Why did they cross the road? Nobody knows. Get to the other side. Okay, so, right, we're going to go through, every time we'll decrement our obstacles, we generate a random row, we generate a random column, right? So go ahead and set that to an X. And I gave it the right number of obstacles we're going to have is going to be 10. Ah. We got 1. Uh-oh. We did something wrong. So we'll just debug it. Let's see what it does. Okay, so row is 0, column is 0. Row is 0, column is 0. Okay, so anybody want to guess why are row and column always 0?
I'm just guessing, but I think where it says dot next double, I think it's either going to be 0 or 1. So if you take 0, 1 times 10, I think that's why.
Well, but if I take 1 times 10, then I should get 10.
Or,
Well, it just so happened that they were both 0.
Or it just so happened, but I did it twice. Like, if you looked at my output, right, it was like,
hmm.
it ran 10 times, and it always gave me 0. Let me try something. Okay, so why was it always giving me 0?
Because you changed the double to an integer as a multiplier.
So I changed the double to an integer before I did multiplication. So now, right, if you remember how it does that, right, it basically lops off all the zeros. Well, the only way I would get anything different is if it gave me the number 1, which going through 10 times on a random distribution, right, mostly unlikely. So what we had to do is we had to do our multiplication, right, so that we scale the number up, and then we want to drop the zeros, right? So, like he said, when in doubt, put parentheses or parentheses it out, right? So I always put in extra parentheses because there are times where stuff like this happens, right, where it doesn't do what you thought it was going to do because the order of operations that it uses is not necessarily intuitive all the time. Now the plus and minus and multiply and divide, right? Those are pretty easy to understand. All right, so now we've got our random maze. Let's look at our maze. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we run it again, right, we gave it a, right, the time, right, keeps ticking. So every time, right, we generate a new maze because that random number generator is always going to give us something different.
Why did we seed it like that?
Why did we seed it that way? That is a general way of seeding something so you always get a different output. If
you just move it and it'll still give you random.
Well, let's see. If we apply our scientific method, let's run it. Let's look what we get. So I got, look at that first row. It does give us something different.
If you leave it blank, I'm pretty sure it just generates anything completely random.
This constructor sets the seed of the random number to a value very unlikely to be. Oh, okay. If you're probably right.
So now it should continue. I can't remember what it does.
Right, so if I give it the same seed, right, it's giving me the exact same output, right? I looked and there's this like little L arcish shape, right? Every time I run it, if I give it the same seed, right, it's going to give me the same output. Now, right, so there are benefits to giving it a known seed, right? Because let's say you want to test something and you want to see like, okay, I ran it and I at some point want to give it real random data, but right now I'd like to be able to test it and see what it does on the same data set over and over again. Right? So then you would hard code it. But, right, using...
You just so happen to put something that changes constantly.
Yeah, so you can pick anything that changes, right? You could have user input. The user could type something. You could use that as your seed, right? Theoretically, right, people won't always type 42 in, so then it'll be different, right, each time. But this is the one that a lot of people use as the current time in order to do that. So, and that's always an incrementing thing. So that's guaranteed, right? Unless my computer time gets reset and it goes back in time and then uses that, which is unlikely because our computers actually update from time servers all the time, which is why actually, let's see. Yeah, they're both the same. If you ever want to know, right, generally your cell phone has the most accurate time because your cell phone provider really cares about what time it is because they charge you by the second. So cell phones, if they're updating, are almost always the most accurate time device that most people have, other than your atomic clock, which also is pretty accurate. So, all right. So next time we're going to talk about, well, On Friday, we're actually going to have a guest speaker and come and talk. He's going to talk about forensics and cell phones. So he's a different speaker than the one that is this afternoon. So we'll have that. So he'll come in it for this class. So we'll have that next time. After that, we'll talk about how we go through our maze.